So the time has now come to tackle the case of quadratic drag when a projectile is encountering air resistance. So we showed earlier that in this case, if quadratic drag is dominating, then this is the differential equation. This is the equation of motion that we need to solve. And we can write that on component form for both x and y, as you already shown. Like that. So this is a system of two differential equations that we need to solve. And it has two properties that we can see. First of all, it is nonlinear. So Vx here exists in nonlinear form in these two terms, and so does Vy. And that makes it such that we can't guarantee that we'll be able to find a closed form solution. Also, it couples Vx and Vy, which complicates things further. So with those two things both in place, it turns out that this is not, as far as we know, exactly solvable. In other words, as far as we know, we can't write down a closed form solution for this, and we will have to resort to numerics. However, that doesn't mean we can't do any analytics. As is often the case, we can look at some special cases of this motion, and there it turns out that we can actually solve this equation. So we can attack the special case of pure horizontal or pure vertical motion. We'll start with pure vertical motion first. And this is now solvable. So now we have, the projectile doesn't look quite like that any longer. What we have now is just the projectile falling down with some velocity v. There's quadratic air drag in the opposite direction. And then we have mg going downwards here. Okay. So in this case now, the differential equation just becomes and that's assuming that the velocity is less than 0. In other words, we're falling downwards if we take y to be in the upwards direction. In the case of linear drag, we were able to find that what happens when something is falling downward under the influence of air resistance is that it obtains eventually terminal velocity. And the same thing should happen here. So we can find the terminal velocity. Now when you've reached a terminal velocity, that means that your velocity doesn't change anymore, so then v dot should be 0. So if v equals the v terminal, it corresponds to v dot equals 0. So if we then take this differential equation and just plug that in there, what do we get? We obtain that 0 equals minus mg plus c v terminal squared, which gives us that v terminal is the square root of mg over c. Okay, so that's the v terminal, comes from this equation here, and the interesting thing is that we were actually able to find this result without explicitly solving this differential equation. So you can actually say something about the solution without really solving it. This is something that is often useful when you're working with differential equations that are nonlinear. And this is in fact known as a fixed point. The fixed point here is that there's a terminal velocity that the solution approaches eventually. However, in this case, we actually are able to solve it. So let's go ahead and do that. If we want, we can rewrite this now as the following. just by factoring out the g and divided by m. And then we can see here that actually looks very similar to the v terminal here. It's actually 1 over v terminal squared, so we get and then we proceed as before, move over dt on one side, all the v's on the other side, and we get the following. Then we take the integral. Now let's say that we start from rest, so that makes things a little simpler, a little less general, but simpler. So this is the first for initial velocity. Present velocity is v. Now we have to put in the primes here to distinguish the integration variables from the boundary. We'll do the same thing over here. Start from t equals 0 by default. Now you may not know how to solve an equation like this or an integral like that, but that's okay. That's why we have integral tables, and we can look them up, and we'll find that actually this integral is equal to r tanh of x. And you can find that by just taking the derivative. You take the r tanh is sinh over cos, and then you can take the derivative and you'll actually find that. So we then make a little change of variables too. We can introduce u equals v over v terminal. So that means that du, actually use primed here because they're inside the integral. So du is therefore equal to du prime is dv prime over v terminal. So we have this integral then. The minus sign there. And that gives us which we can then invert to obtain if you wonder why the minus sign is out here, that's because tanh is an odd function. So I can actually take the minus sign from here, put it in there, and then invert it, and I get that. And if we plot this function, it looks like this. This is a tanh function. And you can ignore the negative part here, that's not important. But we will note that there is that the function approaches asymptotically a value, because that's what a tanh function does, right? It asymptotically approaches 1. So what happens here is that the velocity asymptotically approaches v terminal, actually minus v terminal, so I actually plotted this upside down. But no matter. V terminal. If you say this is minus v versus t, then this is correct. Okay. So that's the velocity, and it behaves roughly the way we would expect it to do. But we also want to find what the position is as a function of time in order to truly solve this. And we can do this by integrating one more time. So we take this equation, now we find that this is actually dy dt equals minus v terminal times the tanh function here. So just like before, you move everything with time over to one side. That's easy to do because everything with time is already on the right hand side. And same thing on the left-hand side. Everything has to do with y there. And then we just integrate it. You may not know the integral of tanh either, but it turns out that the integral of tanh x dx is ln of cos x. Same thing actually holds true if this were regular tangent. It would be minus ln cosine of x. And you can verify that too by just taking the derivative of this. I'm not going to solve this in detail. Well, actually I will, but I won't make any comments while I do it. So that's what that looks like, and we could plot it if we like to. Another way to analyze it is to see what happens at very large values for time. What is the asymptotic behavior of this? So asymptotically for the velocity, it was easy. It just becomes a constant. But what happens for y? Well, let's say so t goes to infinity. Then that means that cosine hyperbolic of t, or alpha t, asymptotically approaches 1/2 e to the alpha t. So that means that we get, must be a square there. You can see here that this g goes away against that g, this v terminal against one of those, as long as we keep them in here. Okay, so this is the approximate solution, this is the exact solution, and we can see that the approximate solution goes roughly, at long times, it goes as v terminal times time, so the distance increases linearly with time, at long times, but there's an offset, because you didn't start out moving at the speed v terminal, so you don't get quite as far as you would have if you had started out at that speed, which is what this term would indicate. Okay, so that's the solution for pure vertical motion. The next thing on the agenda is pure horizontal motion under quadratic drag. So now, in order to have that, we have to get rid of gravity, of course, and all that we have is a forwards pointing velocity and a force that points in the opposite direction. And then the equation that governs this, as we know, is the following. Although this time under the assumption that the velocity in the x direction is greater than 0, otherwise the sign would change here, right? Now, one thing that's different from the case of vertical motion is that if we take v that equal to 0, that means that we find the terminal velocity, which is 0. So therefore the initial velocity at time t equals 0 has to be non-zero, otherwise we only obtain a trivial solution. Otherwise, it's very similar to before. We get dv dt equals minus c over m v squared. I'm getting rid of the x subscript here. And we start out with non-zero velocity. And this is very simple to solve. This is just going to be there. We'll just rewrite this slightly. So just as in the case of linear drag, there's a characteristic slowdown time tau, except it's not an exponential slowdown. It slows down more slowly. We can clearly see here. And in fact, if we integrate this again in order to find the position, then we get the following. We're still starting at the origin, though. So here we get our suspicions confirmed. We can see that x grows continuously with time, although it grows logarithmically, so it slows down and grows very slowly. But we still have that if we take the time to infinity, then x also goes to infinity. In other words, the projectile never stops. The question I'm going to give you now is, why is this unphysical, and how do we overcome it? So I'm going to ask you something we're going to go through in class. So here's a question for you to answer. Again, this solution indicates that this projectile never stops, which is unphysical. So what assumption did we make that led to this unphysical result, and how do we properly overcome it?